Today we're following up on friction. We're going to look at belt friction, and we'll do a little theoretical development, a couple of pages and that sort of thing, and then you find out it's really an easy application. We'll go through a number of examples and that sort of thing. But what you'll find is relatively simple. One thing I'll note too is the book develops them one way, and I'm going to develop it a different way. So I want you to see both approaches. You might like the book's approach better, I'm not sure. But go ahead and take a look at the book. There's two different developments there to help you learn it a little bit. And what we'll be looking at is flat belts. Okay, so just a couple of things. What we'll be looking at is a flat belt over a cylinder. So this would be like your pulley systems and that sort of thing. And we'll have two different tensions. So when you think about it early, and be careful of this when you look at problems, because we have pulley problems. You remember said we had frictionless pulleys, where we could say then T1 was equal to T2. So be careful when they talk about belt friction. Now T2 will not be equal to T1 anymore. They're going to be different because of the friction. So be careful when you read those problems. You see a pulley, make sure it's a frictionless pulley if you want to make the two T's equal. If it's not, then you might have to consider friction. So just in terms of describing it, we've got the belt going over a portion of that. And that portion is measured as theta in radians. And what we're going to be doing, since we're developing this, is then we're going to look at a small piece of that, a differential element. So that's the belt. And we're going to be looking at that small piece that we've now extracted out of there. We're going to take a peek at that. And now what we're going to do is do a free body diagram of this. And consider the two forces there at the either end of the belt. But because now we're including friction, what we're going to see then is there'll be a component of normal force there that we'll call delta N. And then there'll also be a friction force there. So we're looking at a small enough piece there that it's essentially flat. I'm showing it as curved there, but we're going to assume since it's a differential element, it'll be very small. And then one other thing we need to do is that, of course, we're going to apply equilibrium. We need to get some angles out of the way here. Since we're assuming symmetry, then that point of tangency moves over a little bit there. So each of those forces is going to be changed by a little bit of a delta theta over 2. I think we'll get. That's a chunk of the belt. That's a good point, though. Let's free body diagram of a portion of the belt. Now, one other assumption we'll make is what we're going to be doing is considering motion impending. And what I mean by motion here is the motion of the belt on that cylinder, on that pulley, whatever it may be on there. And what we're going to do is be looking at some limits there in terms of whether it's starting to slip or not. So we're going to be looking at taking that to the maximum there, that mu s times the delta n. As I say, one of the things you're going to be walking out of this class is with free body diagrams and equilibrium equations. So what we're going to be doing is just simply applying the equilibrium equations. And x is implied as the horizontal there. I didn't draw it in. Oh. This wrong. Sorry about that. Again, since we're doing a differential here, I want to talk about this increase. So what we're going to have is T on one side. If it was a frictionless pulley, it would be T on the other side. But because of the friction that we're going to now include, this will be T plus delta T. Make this equation make a lot more sense. Okay, so the first piece is we're going to take our T here. It's going to be a minus per my sign there. And then it's going to be the cosine of that small angle there. Now delta F will be actually horizontal, not drawn very well there, but that'll be because we're, again, considering symmetry there. It's going to be horizontal there, so that piece, but what I'm going to do is now substitute in my knowledge of the fact that I'm going to take it to that limit there, motion impending, so I'm going to take it up to that limit. And then the other side, and that's all the pieces then to the horizontal equilibrium. Now, of course, a number of these things will drop out. We'll call that equation A. So we'll just take those two T pieces out there and leave that. And then consider equilibrium in the y direction. And again, what we'll be looking at then is all the vertical components of these particular pieces. So the T's will have some vertical component there. So basically, then all I'm doing is picking up that vertical piece of that one. Delta n will be completely vertical there because of my symmetry in that particular piece there. And then I've got my T plus delta T. And then just combining all the pieces there, we'll have our equation B. Keep our picture up. Did I miss something? We're looking at a delta theta piece here. And again, think of the perpendicular there. That's going to be delta. If I move this one half over and this one half over, then that'll be a delta theta over 2. Good question, though. The question was, where did the delta theta 2 come from? And again, simply thinking that I'm looking at a delta theta piece here. Let's take half of it and move this over. OK, that's delta theta over 2. My perpendicular, my horizontal, which is perpendicular to that, will rotate then by that delta theta over 2. Same way with the other side there. So a little geometry there, but if people are comfortable with that then? OK, now we can we can substitute into A, because now we've solved for our delta n. We can go ahead and now plug that into that equation there. So all I'm doing is just simply plugging this piece into this equation here. And since we're looking at a differential piece, we can take advantage of our trigonometry there in terms of small angles. What we can now do is substitute in that. So all I'm going to do is just simply plug these pieces into this equation here. This becomes my delta theta. That becomes a 1. And then because of the minus sign there, I'm able to take it over to the 0 side there. Both sides will be positive quantities. Next step. Is I divide through by the delta theta. Oops. Forgot to bring my 2 in there too. So I'm taking the 2 and dividing through, bringing the delta theta over there. And what am I going to do? Integrate? Nah. We're going to just take it to the limit. And what we'll find is as we take that to the limit, my delta t goes to 0, delta t goes to 0, delta t over 2 will also go to 0. And what we're left with is a relationship here that basically now describes that change in the tension of the belt there across that theta based upon a coefficient of friction. Now what we'll find is that we can take this now and play around with it. We can create two different forms of it that are going to be useful in terms of applying to actual problems. First of all, we'll integrate and what we'll find then is that we can create a form. It's not the prettiest integration because we end up with a natural log there, but we can deal with that. That describes basically, again, that tension 1 and the tension 2 that we talked about at the very beginning there, related to that coefficient of friction and then the amount of area that belt is in contact with that cylinder. Spell one of these days. The other thing I can do is, since that's a natural log, I can take the exponential of both sides. My natural log disappears. And I can relate it in that form. So we're going to be solving problems with it. We need to think about how we want to tackle it. So if we're interested in trying to figure out what the coefficient of friction is of a problem, or a very particular belt and that sort of thing. Oh, we got a hand up? Question?
I understand all the math, but I don't understand what we just found.
Well, that's where we're going. Here's the problems. So here's the problem approach. So you're feeding right into it here perfectly. So problems. We're going to have problems in terms of I need to know the friction of that particular pulley or cylinder that the rope goes over, or bolliard. Or I need to know theta, how much of that rope needs to be in contact with that cylinder.
For your integration, shouldn't you be mu sub s t theta and not theta? If you're just getting a theta out, it would be a t theta there.
Oh, you're right. Yeah, I forgot my D. Thank you. Losing X's, I'm losing D's. I'm going to be losing my marbles here shortly. So this is one form. The next form, and the more common one, I don't need any extra commentary on that. The one that you'll most often be doing, though, is trying to find T1 or T2. What's that, how much do I need to pull on that to hold something, or how much do I need to pull on it to get it to move somewhere? Natural log. Sorry. I try to loop my L so you know it's an L and not a 1. But natural log. That sort of commentary is okay. Oh, no, I need my E. Yes, thank you. And that's form 2. Okay, so we'll be looking at both forms and solving problems with them. Couple of rules. Expecting a very exciting ending here to this. Cylinder. Just make sure that has an I. So theta is that area that the belt is in contact with the cylinder or pulley or whatever it is. Most important thing though, it's in radians. So we need to be talking about pi, apple pie. Something to go with our beer. So it's in radians. I see a lot of people putting in angles and stuff like that. You'll end up with some really crazy answers that way. So make sure that you do it in radians. The other rule, so that's rule 1. The way it's set up, T2 is always greater than T1. So we're going to manipulate, and we'll see that when we go through the examples here. You need to manipulate it to make sure that however you're setting it up, that T2 is always going to be greater than that T1. Okay, so we'll look at our first problem there, a relatively simple one. Everybody got it? Okay, so we have this 300-pound block. It's wrapped around this pole that's sticking out of the wall there, basically a horizontal rod. We've got a coefficient of friction, a known coefficient of friction of 0.15, and determine the range of values for P of which equilibrium is maintained. Oh, and we've also been described that it's been wrapped 1.5 times around that pole or rod there. Okay, so what does it mean in terms of the range of equilibrium?
Between static and kinetic.
Yeah, okay, well that's good, yeah. Okay, so we're talking about between movement and no movement. Okay, what are my 2 possibilities of movement? I've got a range, so I've got 2 numbers.
You can move either with the block or the rope.
Okay, so the block going down or the block going up, essentially is what you said. So we're going to either pull on it. How much force do I need to pull on it to get that block to go up? How much force do I need to hold on it to keep the block from taking off on me? So that's my 2 cases. When they say a range, then they usually mean try to find those 2 different pieces. Okay, so essentially what the problem has asked us is finding that impending motion up or down. And what we need to do is get a few things out of the way so there's some information before we can jump into those equations. One of them I call the wrap. Okay, so we got to get the wrap into radians. We can't be using degrees here. One complete wrap is going to be that 2.5. So that's one wrap around the pole. And then I'm going to do it 1.5 times. So I just simply 1.5 times that will be 3 pi. Yes. And then if it's a half, you just multiply half times that and stuff. So that's your rule of thumb there is the 2 pi, and you'll be modifying that.
So then from this, do we just use that we know one tension in the rope?
That's a good point, and that's where I'm going with that. Impending release. Okay, so impending release, does that mean T1 or T2? Which one do I know? Okay, I'm releasing, so I'm talking about my block taking off on me.
So T2.
So T2, is going to be the bigger one, right? Because that's the one I'm going to try to hold it from taking off. So that's, again, this is some of the information before we apply the formula there. We need to get that out of the way. We need to think about those two pieces there. How much wrap do I have on it? And then which do I have, T1 or T2? In that case, then I set up my equation. Like so. So I just simply move my T1 over to the other side there, multiply both sides by it, plug in the information I know. Oh, yes, I'm doing the wrong equation. Sorry. I went down a page. This is the form we want. Thank you. Jamie. Must be the heat. This is the form I want. Thank you. We'll be doing the other one there. So that's the T2 that I've decided is the one I know. So I want to move all the stuff I know over to the one side there. And I just simply plug in the values. It's pretty straightforward at that point. And what I find then is it takes me on the other end to hold that 300 pounds with that amount of friction and the rope wrapped around it 1.5 times. I only need 73 pounds of pull on that smaller side there to keep it from going. Now let's get to the one that I started writing. So when I'm considering now pulling on it, what is it going to take to pull to get that thing to go up? My T1 now is going to be the 300, the smaller. It's going to take more to get it up. Now I can put the equation that I started with. And what I find then is then to get that block to move up, I'm going to have to pull on that other end there, 1,233 pounds. So my range of equilibrium was what the question was asking us then, will be basically that 73 through 1,233. If t ranges anything different than that, basically the thing takes off.
Which one is the T1? Which side is this certain side of the road?
It changes depending on the equation, see?
Okay,
Is that making sense there? So when we're thinking about going the one way, then the bigger value will be the 300. When we're trying to pull it up, the bigger value will be what I'm pulling on. So the T1 will be the 300. Question?
So in this scenario, we found T2 first, and then we made T1 equal T2, and we solved for T2 that way to get the other side of the range, right?
Yes, essentially, yeah. We used what we did was we used the form like so. And what we did was just simply played around with these T1s. And that's why I say we have to do a little work right before we dive into throwing the equation at it. The equation is really simple, but you need to think about how to apply it. So when you think about impending release, in other words, it's starting to go down, then the biggest value, which is T2 always has to be the bigger value in terms of the way this equation was set up. I'll put my 300 here. And then T1, which is then the smaller amount, basically, this is all I need to keep it to go. And vice versa then when I looked at the other way. So it's easy formula, just be careful with the application.
Why would it only take 73 pounds to prevent it from going down, but 1,233 pounds to start pulling it up?
Friction.
That's a huge difference.
It does, yes, yes. Well, and that's why, I don't know if any of you have ever sailed, but if you ever used the bollards and stuff like that when you're pulling on the sails and stuff like that, it's amazing how you can just wrap it once or twice around and basically how much force you can actually deliver.
Imagine we pull it up, like as you pull the block, that you're also finding gravity to the thing, the gravitational force actually against it increases proportionally.
Yeah. Well, and where the trick is, let's go back to our equation. Remember, when we were looking at this, we were looking at this piece of belt here. As those T's increase, so does that normal force then. So you start increasing it basically, but I guess that doesn't necessarily answer the friction question. Well, and you know, if you've ever been to a port and that sort of thing too, you'll see these big ships being held basically with their the bollards there. And matter of fact, we'll look at a bolliard problem right here. That'll be the next problem that we look at here. But again, it's amazing the amount of friction, because once you start wrapping it around there, basically you're adding force there, you're adding normal force to that, which is creating higher friction force, basically. And it's pretty amazing how much you can do. As a matter of fact, when we talk about this one, we're going to jump from 5,000 pounds to part B there. We're going to look at 20,000 pounds being held with just an 80-pound force. So this problem is a little bit different. We're going to be looking at a different form there. But we've got, in terms of this problem, we've got known forces. So we've got an 80-pound force, which is Joe Dockman there holding the boat in place there. We've got a massive liner there, and he's holding it in place with his 80 pounds. And resistive force of 5,000 pounds on the other end. So what we're going to be asked for in the first part of this is, okay, well, what sort of coefficient of static friction do I need between the rope and the bolliard there, basically, to keep to be able to maintain that 5,000 pounds? And then the next question, which is a little bit more fun, is okay, well, now the ship's going to put a 20,000 pound on it. The guy can only put 80 pounds on it. How many times do I need to wrap it around? So we'll go and look at that case too.
Then you have to look at too how strong that actual piece is, like connected to the wood.
There's that's mechanics of materials. We'll get into that next in a semester or two. But yes, yes. as an engineer, you can't just look at the friction. You've got to be looking at the whole problem.
It's like the same thing as the last one. Like if that joint, that wall joint couldn't hold, if it wasn't like welded well enough, it couldn't hold 12,000.
That, or if you, as we learned in moments, if we take it way out there, it's a big lever. All of a sudden, you got the issue of it breaking even easier and stuff like that. So yeah, how far out do you put it? So we're going to make engineers out of you. So when you're working on your house and you're pulling something up, make sure that it's close by there so we don't lose that particular piece. So again, we'll think about what form we're going to be looking at. So what we're interested in now is looking at coefficient of friction, and then the second part we're going to be looking at theta. How many times do I need to wrap it? So we're going to be using this form of the equation, and then again we need to start thinking about what information do we know. So A So it's going to be 4 pi. We know it's wrapped around twice. And then the other two pieces that we know is T2, which is my 5,000 pounds. My T1, which is Joe dock worker, and his 80 pounds. That's all he could muster to that for that day. So just simply apply our equation. What we're going to do is to take our theta now over here and put all the known on that side. And the one thing I'm looking for then is my mu of s. Somebody already do this? And straightforward, basically what it says then is I need a coefficient of friction for that particular piece of about 0.33. Easy application. Again, just keep track of what you know. Okay, now part B is asking us now we're going to increase that force. The one bit of knowledge that we do have now is what we've already created there. We know that it's going to be the same Bolliard, so it's going to be the same coefficient of friction. So we have that bit of information. And then basically our dock worker still will be the smaller of the two there, so he'll be our T1. And we're going to increase it now to 20,000. And our equation will look like that. So we'll just simply solve it in terms of the theta. And then what we're going to do is solve for that. But again, remember our theta is measured in radians. So we've got it now in terms of radians. But Joe dock worker wants to know how many wraps. He doesn't calculate radians. So he needs to know how many times he needs to wrap it around there. You're too fast. That's why I crossed my 7s and I still can't see them. Okay, so I just simply divide the number of radians by 2 pi, which is a single turn. So basically, you'll tell them 2 2/3 turn, basically, or run it up to 3, 3.5, whatever works out for him in terms of where he's standing. So simple application. Lose that already. One key point here, too, in terms of applying this is if you do take your EIT exam, the FE exam, there'll be a lot of problems on it. These are just the easiest ones. You can just dive right into them and solve them. We'll look at the next one here.
You said T2 is always greater than T1, right?
Yes. Did I put it somewhere wrong? That's our general rule. T2 will always be greatest. So that's the bigger number. That's just the way we develop the equation. So it's not necessarily because I said so. Now we'll get on to a mechanical engineering problem here. A little more interesting. To get you guys excited. So we've got a power system here. We got a power belt down here at B here that's going to be inputting some sort of torque into our A there. And again, we know the coefficient of friction of both pieces is going to be 0.4. And the allowable belt tension is 550. So if we go above that, we might break it. So we don't want to go there. And basically, what we want to do is figure out what is the largest couple that we can put on A, the largest torque. And given the sets of dimensions there and radiuses and that sort of thing. So again, simple application, but we need to kind of think some things through and do a little bit of geometry now because it's not easy 90-degree turns and that sort of thing. Okay, since the coefficient of friction is the same on both, which one will it slip on first?
Depends which way it's rotating.
It's not on that.
I guess that's right, yeah, smaller one with
Yeah.
less surface area.
The pulley that's had the less belts. Now, does that fly in conflict with our, remember we talked about friction way back when, where we said contact area it's independent of contact area? Is that an issue here?
Yeah. It's not independent of degrees, and it has more degrees of friction, I guess.
Yeah, so why could I say that the one that has the less belt contact when we talked about belts not having? What was the question? Or the?
Well, it goes through a higher angle. It goes through more of the circle than the top one does.
Uh-huh.
So it's a bigger angle.
It's bigger angle. Mm-hmm. So our equation, yeah. So you're thinking of the equation and like, oh yeah, that's bigger, so it will be bigger. But let's think about what that means. And where I was going with that in terms of the contact area there was, as you remember, this was T. This is our T plus delta T. What else? Oops. What else is increasing as I increase that belt area there? That. So as I'm going round and round, we talked about that a little bit earlier there too. The more I get wrapped there, it's not necessarily the contact area as it is the fact that I'm increasing more normal force there. As I start going more and more around there, I'm getting more and more normal force, hence I'm creating a lot more friction force. So it doesn't really fly in the face of that rule, and that rule still holds in terms of basically contact area is independent, or the friction's independent of that contact area there. But the only reason we can say that in this particular case, though, too, is that we know the coefficient of friction is the same for both pulleys. If it's different, and if we have some time, we'll go through that exercise there, too. If it's different, then you've got to look at both of them and see which one actually is the worst. So in this case, it's B. Now, one of the things we're going to have to get out of the way is figure out what my wrap is. So the belt kind of looks like that. And remember, this angle here is not going to appear with that color. My goodness. Okay, so we got that 15 degrees. So that was kind of the interesting thing about this particular problem. If we think about the fact that if the belt was perpendicular, straight perpendicular there, out of there, so that was 0 degrees, I could draw my point of tangency there. What I'm saying then is then if the belt was straight like that, and matter of fact it should be straight like so, if I'm rotating the belt on this plane by 15 degrees, then this angle will also be 15 degrees. Okay, if my belt was straight, so it's the blue line here, right? My point of tangency where the belt releases from the pulley is going to be right there at the horizontal point there at 90 degrees, right? Now, what I'm going to do is I'm saying I'm rotating my belt 15 degrees. What that does is then changes my point of tangency by 15 degrees on that plane there, which is still that perpendicular.
It's like you're just taking that L and just rotating it.
Exactly, yeah. So just take an L, rotate it by 15 degrees. Same thing with the other side there too. Now I want to make sure everybody's comfortable with that before we go on. So now that's less area of contact on that particular belt there, and it gives me the ability to calculate that. And I just simply, I'm going to lay out a ratio here that pi is to 180 degrees or 2 pi is to 360, whichever you want to do, is equal to alpha is equal to then the 15. So basically my alpha will be pi over 12. And what I'm really interested in then what I'll call beta. Oops. Beta would have been 90 degrees, or pi for the whole 180 there. I'm going to subtract off those two 15-degree angles there, and basically I end up with then my wrap area in terms of radians is going to be 5 over 6 times pi. Okay, so what I'm going to do is take it up to the limit there. We're going to look for that impending slip on B, which is the one that has the less wrap on it. It's going to be the one that slips first. Oh, it's not pounds. right, yes. Okay. So if I'm looking at pending slip, then basically my biggest value is going to be that 450. I go beyond that, then the belt's not going to be very happy. It might break or something like that. So my bigger value will be that. What I need to do is now find out what that T1 is, the smaller force on the other side there. Actually, since I'm calling that beta, we'll just call that beta. And then we go through and calculate then the smaller end, or the less force end of the belt there. That T1 will be about 158. Okay, and then this actually turns out to be pretty simple. What we're going to do is calculate the couple on A. So we'll draw our free body diagram of A there. I'll get some pens that actually work. Okay, so what A is seeing then is this belt, this T1 and this T2. So I've taken my pulley B up to the maximum where it's going to start slipping basically, and I'm not going to be able to provide any more power to A. And it's just simply applying moments there. So I'm going to take my moment. The nice thing is I'm going to take it at A there, because my radius, no matter where my point of tangency of T1 and T2 are, they can be rotated anywhere basically. It's always going to be perpendicular to the radius.
10 millimeters too.
And the one force I didn't put on there is that couple that I'm looking for. And then again, in terms of, so what I'm going to do is my T2, did I do that right? Sure, I've got my, oh yeah, because I've moved my M over. That's right. Okay, so my T2 times the radius, where it intersects basically, it'll be perpendicular there at the, where it connects, or the tangent there at the pulley, minus the smaller force on the other end there. And what I find then is this is the couple that I'm able to, the highest couple I'm able to transmit to that pulley A. Question?
Is the tension always going to be bigger on the side, but again, that the dependent, that would be pulling toward the intended motion. That's what the glue arrow is, right?
Well, it's basically saying this is the way the wheel will turn when I get going. So I'm not looking at impending motion here, though, not yet. Yeah, I'm looking at impending motion on B because I'm taking it up to the point where it'll start slipping. A, I don't worry about because it is the same coefficient of friction, but a greater wrap. So it's not going to slip. I don't have to worry about that yet. We'll do that next, though. Question?
Do you care which way it's rotating at this moment?
Yeah. I could, T2 could be the other way, too. It doesn't matter. Oh, question.
For the tensions, they're perpendicular because you can't get the pulleys to have contact past 90 degrees, right? Why are the tension 1 and 2 perpendicular to the third?
Well, it's that same issue there that we had before there. If we, let me draw it a little bit better here. Remember, if my belt was straight, it would be like so, right? Now it's it's over 15 degrees because it's basically connected to the other one there. Again, that'll be 15 degrees that way to catch, well, the arrow that I actually have there. But again, that is got to be perpendicular, right? That's my point of tangency there. So the radius, my moment arm doesn't change because wherever the belt releases, basically the perpendicular is always going to be that radius. Does that convince you?
It's saying if it goes past 450, what's happening? Is the belt breaks?
Well, it says that's the highest that you're rated with the belt. So yeah, the belt might break or something like that. I'm not sure exactly what he's trying to get across there. He's just.
So those pulleys are moving, and they're just moving that belt around. I don't understand what would happen if it had too much. What's the problem with it?
B is your motor, your engine or something. It's transmitting coupled to A.
Yeah.
And because they have the same coefficient, it has less wrap on it. It has the potential of slipping because we have a coefficient of 0.4. And what we're saying is okay, the author came up with 450, and I'm not sure whether it's belt breaking or whatever, but that's as much as the belt can take. So we're saying, okay, if we're going to do that, then we need to figure out how much couple I can get into A without the belt slipping on B. Mm-hmm. Now what we'll do is go a little bit beyond that. We're going to consider a different friction on A, which means in this particular case, we could stop here. We don't need to worry about the checking to see whether belt or pulley A slips because it's the same coefficient of friction as B and it's got more wrap. So question over with, we don't even need to check that. Now, if we're given consider get my black here. We'll consider a case where the friction's different. So we'll consider the coefficient of friction now on A as less. So maybe they drop some grease on it or something like that, and it's not doesn't have the same coefficient of friction. Now we need to go look at it to see whether we've calculated B already. So that doesn't change. We've already calculated that. It's 0.4, and we've calculated the values on either side of that particular belt that it can generate. So what we're going to do now is because A has a different coefficient of friction in this particular case, we're going to have to look at A to see whether A slipped or not. And basically applying the formula in the opposite sense there, since we know that it's wrapped a little bit more, and it's going to be that pi over 12 on either side there, we'll just simply add that. And what we find is then the amount of wrap on that one is going to be 7 over 6 pi. Now, before we go there, let's check and see what we have in terms of information now. So we've got how much wrap is on there. We know the coefficient of friction. We've got our T1 and our T2 that were being applied to this. So basically, we actually have everything, and it's like, well, okay, well, what am I going to check? Well, one of the things we can check is, let's see if the coefficient of friction is sufficient. So we'll do mu of s for our A. So I know my coefficient of friction is going to be 0.25 on that. So what I'm going to do is check to see, one of the ways I can check is to see basically whether that coefficient of friction is met or not. It's the heat. I've read too much beer too, I suppose. Okay, what we'll find is that in order to have a T1 and a T2 of the values that B can provide me without slipping, I would need a coefficient of friction of 0.286 in order to be able to carry that couple. Unfortunately, that's greater than what I have on there, which then implies that A will slip first in this case. So let's figure out what this couple is by figuring out what level or what that T1 is basically when I start slipping on A. So what I'm going to want to do now is calculate this new T1. Now the key thing here is when I put this in, when I solve for this one, I'm going to put in the actual coefficient of friction on A. I'm not going to put on this one that says that if you're carrying that couple there, you need that much. I don't have that much. I have 0.25. So I'm going to go ahead and plug in my 0.25, which then says I have 180 newtons. So we've reduced that. So that's the one case. You don't have that in the homework example there, but if you've got two different frictions on those pulleys, then you need to account for the fact that you need to check for both of them for slippage. Now, anyone puzzled by the fact that that number 180 is bigger than the 157? No? Time to go home then. Did I do something wrong?
I said positive or negative. Yeah, you said you didn't care about the direction of the spin.
Oh, okay.
Yeah. I wasn't worried about direction, basically. So it was just basically calculated. We don't know which way it's twisting. But one thing to consider here, if the pulley A was frictionless, which we will have problems on that, so make sure you remember that, T1 equals T2 equals the 450, right? So just think about it in terms of that term. If it's frictionless, then basically we're not going to get any couple into it. And by the fact that as we start increasing that friction from 0 basically to 0.25 there, then what we're going to see is then our 450 dropping. But again, that's going to be all I can get in there without the pulley A slipping.